last day, right? So like primarily how to compute the distance in between the transceiver and the in between the transmitter and the receiver, right? And we, as we sort of discussed, was distance is basically the time of arrival. This time of flight is also sometimes called the time of arrival, time of arrival, or TOA, right? These are used interchangeably, and multiplied by c, which is the speed of light. Okay. And one more thing that I mentioned was that the precision that is required for computing this time of flight, so the granularity of computation of time of flight has to be very fine grained. Okay. So this computation has to be very fine grained. Okay. And what do we mean by fine grained? What is the how many ticks, what is the distance in between these ticks that we actually require, that will suffice a decent localization application, right? So what is the length of this particular tick, what is this delta t? Okay. And since we have already known that the distance is basically time of flight multiplied by speed of light, there is a lot of scale up, right? And since we know that this radio waves is going to travel 1 feet per nanosecond, so at a nanosecond resolution, you are already going to make an error of 1 feet, right? So if you are computing your time of flight in, let's say, microseconds, or even like zero point 0.1 microsecond, like hundreds of nanoseconds kind of a resolution, that is also not going to suffice, because just delta t, think about it, is delta t is like, let's say, 1 microsecond, right? Which basically means that in within, if you are trying to compute the time of flight, let's say this is tick number I and this is tick number I plus 1, right? So if the distance in between them is 1 microsecond, the distance that will be computed, the physical distance that will be computed, is like 1,000 feet, right? Which does not make much sense in the context of indoor localization. We are trying to look for like feet or even less than a feet. Okay. So we have to keep this in mind, that why it needs to be fine grained, and we are looking at like sub nanosecond sort of a resolution. Okay. So, and that is the reason it sometimes can become a very hard problem, right? If you want to implement ranging, let's say, right, you have to keep all these things in mind, otherwise you will get something which is completely weird, right? You will get some numbers which will run in kilometers, right? So, and it will not make much sense in the context of localization. Okay. So we started with a very simple algorithm, and it's already discussed that since we do not have proper synchronization of the clocks in between the receiver and the transmitter, we are going to run into a problem, right? So the simple algorithm where we record the timestamps at the receiver and at the transmitter, and we just take the difference of that, right? That row basically is your time of flight, that multiplied by c is not going to give you an accurate value of the distance. Okay. So moving forward, we discussed four primary challenges, right? And I'm going to put them all together, right? So there are four things. One was the processing delay between the time when the packet was time stamped and the packet was actually sent out, right? So, and the same holds on the receiver side. The packet would be received first, and after a certain delay only it will be time stamped that, hey, this is the time at which the packet was received, right? But it's not exactly the time when the packet arrived, when particularly we are talking about nanoseconds or sub nanoseconds level, right? You have to remember this is the operating system, or there'll be some hardware latency that will be involved in doing that. Okay. And the other thing was the clock offset in between the two devices. So we have to either like we did in GPS, we have to take care of this separately as a part of the range equations, or just to remove all such hassles, can we have an intelligent ranging mechanism that will take care of this clock offset in between such devices. Okay. And number four is basically we are trying to clarify our inability of applying point 1 and point 2, right? So instead of explicitly time stamping on the packet, will there be any mechanism that can give us a very good idea about when the packet exactly arrived, of course in the granularity of whatever we anticipate, right, around nanoseconds and all. And how does it like, on what factors does this capability depend on, right? Whether you would be able to process the packet arrival time in terms of nanoseconds or in terms of picoseconds, what does it depend on, right? So those kind of things we would like to explain as a part of today's session. Okay, so primarily your takeaway point would be you have a good understanding of how ranging takes place in between two devices. In the last two classes you already know that if you knew the range you can do a lot of things, right, including you can do all this localization, but the starting point, before you do the localization, you have to start from this ranging primitive, right? This is like your Lego block. Without this Lego block you cannot build this house. So you have to know how exactly ranging takes place. So let's try to address these points one by one, right? What we can do about them. So one idea to solve one and two, right? You have to bring the time stamping procedure as close to the network interface card as possible, right? So if your operating system is actually trying to write the timestamp, maybe you have to now write the timestamp in the hardware itself, right? Maybe in the network interface card, you have to have a mechanism in which the packet is time stamped. Okay, so it's no longer being done in the software, it is going to be in the hardware side, so that can reduce the latency. Okay, so one more thing is because we don't want any uncertainties, right? So yesterday there was some discussion about uh, frequency selection, and somebody said that there could be jamming, right? So I just clarified that uh, it's kind of packet collisions that you might see, right? And those kind of uncertainties are not going to be considered here, because if you have that kind of uncertainties, you will have a lot of uncertainty in your TOF estimation. So what we try to do is not basically do carrier sensing, right? You all are aware of medium access control protocols, right? Where in the wireless medium we try to do carrier sensing. If we see the medium is busy, we defer the transmission. If we see the medium is idle, we try to transmit, right? So then there are backup algorithms and so on. So in this case, there is no question of carrier sensing, because this is so much related to the time of transmission, the exact point in time where you when you transmit. We don't want to do all this backup algorithm and have this randomization, because this makes the entire system very, very complex. Okay, so what we do instead, this is a tightly scheduled system, right? In most of the cases, as we'll see in ultra wideband UWB radios, right? We are going to tightly schedule the system. We are going to tell those nodes, let's say 1 and 2, at time t, some time t is equal to t1, 1 is going to range with 2. At time t2, 3 is going to range with 7, and so on, right? So this will be a tightly scheduled system. There are, like, we don't allow any chances of collision, because we are telling them when to transmit, what slots to choose, and that is the reason we don't perform any carrier sensing. Okay, so there is not much of a uncertainty involved. Okay, for the transmissions. So for doing this, right, what best we can do? Okay, so I have already told you what is the big deal about it, is because how much fine grained we want to be in order to really have a range that is acceptable by your localization system, right? We are not looking at kilometer level accuracy, we are trying to look at meters or sub-meters or feet, right? So a network driver already can give some timestamps, right? If you look at the packet headers, there are options in the kernel in which you can actually get such values, right? But that is often far from accurate, right? Because it although gives you some, you can see this value that is quoted here, right? The software timestamp, I'm writing this TS0, TV underscore second and TV underscore nanosecond, right? So although this reports a value, this is often far from being accurate. Okay, because the kernel does a lot of other job scheduling, right? And the time slots might not be that granular like nanoseconds, right? So that can easily screw up the value that you are going to get, right? And apart from that, you will also have clock drifts. So the value that you are going to get is going to be far from the actual timestamp that you are actually anticipating. Okay, so you can look up some of the network driver codes, right? If you have familiarity with the some of the this kernel and the device drivers, right? You can actually just for your interest, you can try to look at how can timestamps be extracted from the packets when they go out and when they come in, right? And that will give you some idea about how this can actually be implemented, right? I've shown you a code fragment, but you can delve deeper to understand this, right? But the bottom line is we cannot use this because this introduces a lot of error. Okay, so now we are going to go a little bit deeper into the estimation of the exact packet arrival time. Okay, and for that we need to understand a little bit of the physical layer, how a signal is processed or how a signal is modeled. Okay, so when there is a transmission, right, from the transmitter to the receiver, in time it is going to see a series of amplitudes with time. Okay, so let's say there is an impulse. So what is an impulse? Impulse is like, let's say, a gunshot, right? That is like an impulse that is suddenly created. Okay, or I speak, right? So somebody has created this sudden fluctuation of amplitude in time, right? So that is something that is being created by the transmitter. So the transmitter creates an impulse. So when any packet is going to be sent out through the radio, right, there will be a sudden this impulse will be created and you will have a power spike, and that spike in power or amplitude is going to be reflected on the other side, so after some time, right? And that is exactly what I have shown. So that is known as the impulse response. Okay, so you have an impulse that was created by the transmission of the packet, and on the receiver side you have a response to that. Okay, so I speak, let's say this is a human being, and he shouts, and after some time somebody will hear this, right? So in his ears he will hear the response of that particular impulse. Okay, so it's very similar to our wireless systems as well. But the thing is whether you are going to hear only one impulse or not, right? Let's say you have these reflectors, right? You have these walls. So what are these walls going to do? The walls are going to also reflect this sound wave or this electromagnetic wave that we are considering, and as well you are also going to have this direct path from the transmitter to the receiver, which is often we call it the line of sight path. Okay, so this will often be called as the line of sight path or the LOS path. Okay, so there are no obstacles in between the transmitter and the receiver. The signal that you are transmitting very happily reaches the other side, and within this time tau or t, right? So within, let's say, this time tau, and you have an amplitude, right? This is the amplitude that is recorded at the receiver, this channel impulse response, or the CIR in short, that is recorded at the receiver, and you will see a certain amplitude. Now what will happen? There are other paths. Okay, so the signal not only just travels through the line of sight path, because this is a signal that is just broadcasted in the air, right? So it is just this is just raw power that is put on in the environment, right? And the signal is going to travel in many different paths. Okay, so and some of those paths are going to face obstacles, and it is just going to follow the rules of optics that you have already studied. It is just going to, it's just a regular electromagnetic wave, and it is just going to bounce off those particular obstacles, right? And of course it will be reduced in power, as well as so that is the reason you will see a lower amplitude. Okay, and similarly you will have another path, let's say, right, which is still more of a lower amplitude. Okay, so now what is interesting here is that I have drawn this red line first, right? I have shown this one as the first amplitude. The gray one is like the second amplitude that has arrived in the receiver, and the yellow one is the third amplitude. Okay, so any idea why they will be coming at different points in time? Why is the time increasing, right? And then amplitude we have already discussed, because it is facing some obstacles, it is reflecting bouncing of these obstacles, and in that way it is losing some power. Okay, so some power it is losing, and that is the reason the amplitude is becoming lesser and lesser. But why does the time shift? Why do I have different timestamps for these multiple amplitudes? Like why this is tau 1, why this is tau 2, and why this is tau 3? Okay, the line of sight is, this is tau 1, this is tau 2, and this is tau 3. Any answers from the participants?
Sir, the line of sight path is the shortest and
Path difference.
Path difference. Very good.
Multipath, due to multipath.
No, multipath is a phenomenon, but the exact answer I have already gotten, right? So that is because you are traveling multiple different path lengths, right? So the line of sight path, right, which is basically the shortest path, is going to always take the shortest amount of time. And if you are going through very circuitous routes, you are going to take longer time. Okay, this phenomenon is known as multipath. Because if you have so many obstacles, I might be seeing so many amplitudes in our impulse response, right? And why do I use the word channel? The word channel primarily in this context, right, it is going to describe the state of this medium here, right? So the transmission medium is it has a lot of obstacles. The environment is being reflected in the channel. Okay, so what are the positions of the obstacle, what are the obstacles, whether there are any obstacles or not, right? That reflect the channels quality here. So in this context, in between the receiver and transmitter, whatever happens, right, that particular in an abstract form, it's kind of a pipe, right? So that, what is the impulse response that is associated with that pipe? Okay, and that is what we pick up on the receiver side. Okay, so very clearly, based on whatever number of obstacles you have, you will keep on having such amplitudes, and after a certain point it is going to die down. Okay, so that is the, like, the dwell time or some coherence time we can think of, right? So within that particular time, that will be at least required to register the arrival of the packet. Okay, and after that, after a certain time t has passed, I will no longer see any fluctuations in amplitude. It has completely died down. Okay, so very similar thing you can observe if you go to a place where there is a lot of echo, right? You cannot speak continuously. Like once you speak, you have to wait for the amplitudes to die down, right? And you have to give a certain time, and once that is done, then only you can speak, right? Otherwise what will happen, before the amplitudes from the previous impulse has died down, you have started talking again, right? So there will be a lot of interference in between the multipath arrivals, right, with your new uh, arrivals from the second one, right? So you want to start, then you'll start overlapping. Okay, so you have to wait this particular period of time based on the multipath environment you have to, for the signal to die down, then you start transmitting again, right? So the, what our interest is, can we analyze this information and try to understand what is the line of sight path length? That is what we are interested about. That is what is known as range. That is the LOS path length. Okay, that is what we are solely interested in. We don't have any other interests. And there are many side things that you can do with such impulse responses, that for example you can try to model the environment using this, right? So if you get access to this channel impulse response data, this data can be used to model how many obstacles are around, right? Those kind of things you can do. So there is one more thing that you have to also understand, that there might not be a direct line of sight path. There could be an obstacle, and maybe the obstacle is can completely cut off the signal. That is possible. So in that case, you will not have any amplitude that is corresponding to the line of sight path. You will only have this in-loss paths, right? This is non-line of sight. Okay, and the line of sight path could be completely cut off. That is one option. And the other thing that you might also have is basically a weaker copy. Maybe it is going to pass some of the power that was emerging from the transmitter, and most of it is absorbed by this obstacle, right? This is, let's say, some wooden furniture, right, that is just in front of the transmitter. It is going to take out a lot of power from that incoming signal, and it is also only going to pass through a little bit, right? And that is why you see that although in terms of, it is not going to delay the packet, right? It's not going to delay the signal, right? So yesterday also there was a discussion about the SNR or the noise and the time of, because the signal is going to travel in the same speed. It's not going to reduce the speed or anything. Okay, so by the time it reaches the receiver, it is still going to come at a time tau 1, right? And the others will be delayed copies, tau 2 and tau 3. But tau 1 now is going to have an amplitude that is lesser than the other in-loss paths. Okay, so this will be surprising, because you think that the first strongest path is going to give you the signal that came through line of sight, and you might be mistakenly, you can start thinking that this gray is basically your line of sight path, right? This will be your sort of a false positive, right? You think that this is the line of sight path, that is the amplitude that is corresponding to the line of sight path, and the time of arrival is actually tau 2. But you will be mistaken, right? Is actually this is the red one, the at tau 1, which is your line of sight path, but that could be sort of smeared because of the presence of these obstacles. And you can understand how the multipath environment sort of tells you or dictates the quality of your ranging, or the precision of the accuracy that you are actually able to obtain from the this ranging procedure, right? So if you have a lot of different obstacles around, if you have lots of multipath, you are going to see the ranging quality getting deteriorated, and that is the reason you start having range errors. Okay, so instead of T1, let's say you choose T2, so you have to basically your ranging error would be T2 minus T1 multiplied by C, right? So this is going to be a ranging error. Done a mistake, right? Ideally it was tau 1 into C, so some meters, but you thought it is tau 2, so you basically compute as that tau 2 into C. So your error would be tau 2 minus tau 1 multiplied by C, right? And this tau 2 might not be the immediate next one, it could be like far off. Okay, so now you are starting to get an idea of how this wireless ranging takes place, and what are all these channel impulse response components. Okay, so what we see mathematically, right, is basically every amplitude here, right, every component here is basically a delayed copy of the signal that was originally created. Okay, so first one you always see, this is the first one, this rho 0 into e to the power j phi naught. This is basically the phase, right? And at every time slot we are going to receive a delayed copy of the signal, right? And I already told you that there is this dwell time in which we are only going to concentrate on, and after that we assume that the signal has died down, or the impulse reflections of the impulse responses no longer exist, or the amplitude is so low that we can ignore. We can go ahead with the next transmission. Okay, so let's say we have this endpoint time series, and all of them will have some value of amplitude, right? So this is basically the impulse response. Ideally the first one is the line of sight. Not ideally, always this will be the line of sight. It's just that depending on the amplitude of this component, right, depending on the magnitude of this component, I will not say just amplitude, magnitude of this component, we might be fooled. We might start thinking that maybe tau 1 or maybe tau 2 is the first component, right? So there could be some kind of misleading information that we might get. Okay, so I hope this particular part is clear. And the good news is that some hardware, as you will see very shortly, gives you access to this channel impulse response. So if you have access to this data, right, that is golden, because that will tell you from that particular data you can find out the first peak. That is what you need, right? What is the first, I would say, I'll put an inverted comma, first significant peak. So if you know the offset of the first significant peak, you know basically the time of flight or the time of arrival of the packet. Okay, and we will see like some hardware that you can actually buy off the shelf, and that has registers which is going to give you access to such data. Okay, and the reality is a little bit different than you saw, right? It's not as clean as this. This is too clean. Okay, but if you actually collect such data, you will see something like this, and that will have a lots of local maxima minimas. Okay, and that is going to make your peak detection problem a little bit more difficult and tricky, right? So there are, as you can see, there are many peaks, right? This could be a peak, this could be a peak, this could be a peak, right? This could be a peak, this could be a peak, right? So which one to choose, right? That itself can become a difficult problem with the extraction of the first peak or extraction of the time of arrival data from the channel impulse response, right? So channel impulse response is this, there is no doubt about it. Okay, in the x-axis we have nanoseconds. So in 250 nanoseconds probably is the dwell time, and within 250 nanoseconds everything has died down, that is for sure. So you can guarantee that your distance is not more than 250 feet, but you are not happy with 250 feet. You want to know whether it's 50 feet or whether it's 100 feet, or and so on, right? Because if you choose this peak, right, this is 50 nanoseconds, which is going to be like 50 feet, right? And if you choose this one, right, this could be 40 nanoseconds, which is 40 feet, right? So by just choosing a different peak, you might end up having a range error of 10 feet, right? And we want to make it as better as possible. Okay, so this is the exact thing that I just now demonstrated, which one we should choose. Okay, it could be that the line of sight path was blocked by a certain obstacle, and that does not mean that you are going to. So as long as the localization is concerned, we need the exact value of the range, right? Doesn't matter whether there was a furniture in between your transmitter and the receiver. We really need the exact range in order for the geometry to work, right? The range could have some noise, but that noise is not going to perturb the entire geometry. So instead of 5 meters, if you tell me it is 10 meters, then it is the geometry itself changes, right? So in that case, your LM algorithm or any other algorithm that we learned about is not going to help you, right? It will be completely thrown off. Okay, so I hope this concept is clear, right? And often, as I told you, right, we are more thinking about this 1 and 2. It could be that maybe this is the first path. There's a small peak here that I have zoomed up, and this could be the first path. Okay, so then you'll be like off by maybe 20 feet. Okay, so so this is still an open-ended sort of problem, right? There is no like standard, like there are some standard solutions that I am discussing here, right? So that is the way you should approach the problem, but there is not one algorithm that is always going to be better, right? And now many different vendors who are actually producing these chips for many different technologies, it could be ultra wideband, it could be Wi-Fi, and so on. That is their patented algorithm that is going to be used in order to calculate the exact packet arrival time, and often these are proprietary algorithms, right? So in the nutshell, I told you what the problem is about, right? And you can always write your algorithm. There are many peak detection algorithms available. You can use one of them, and it might work in some cases, it might not work in some cases because of this uncertainty, right? This noise. So not all of them are going to be legitimate amplitudes obtained from this impulse response, right? There could be noise inherently present. Okay, initially also there could be some noise because initially you might not receive the signal, right? You have to wait for some time. Okay, so and then you start seeing the signal. Okay, so for that, this is sort of an open problem. How do you understand that it is no longer noise? I have received the first peak of the uh, corresponding to the impulse response. How do you identify this, right? That is how you calculate the exact packet arrival time. Okay, so there is no software involved. This is primarily an artifact of any wireless reception. Whenever you receive a signal in the radio, this is going to create it is going to manifest itself in this way, right? So within a certain period of time, you will keep on seeing this amplitudes going up and coming down. And if you record this video, right, if you record this information like a video, by analyzing that, you can understand that what was the first peak or what was the sometimes they will also, instead of taking only one peak, there are some algorithms often like proprietary, but they have discussed what basically they can do potentially is they can, instead of considering only one peak, they can consider multiple peaks together, and at the same time they can also take an average of that. Okay, uh, there are other techniques. If you have many peaks, right, instead of the CIR which looks like this, it can also look like this, right? You have many peaks. Okay, then the CIR algorithm is going to be really confused, right? Which one to choose, why there are so many strong peaks. And often they are also going to look at the number of peaks like that are like of high value, and based on that they can also create an uncertainty metric. Okay, so this is going to tell you that, okay, I think that the first peak is the second one and give you some kind of time of arrival value, but I see so many peaks that I am really uncertain, right? If you just see only one peak like so clean, I can be 100% sure that maybe this one is the first path, right? Maybe this is noise, and this is basically your I mean second strong path. Okay, so, but this kind of situation is very rare, right? It's very difficult unless and until you go to an open space where there are no reflectors, you place the transmitter and the receiver high up from the ground, then only you can try to recreate such a clean CIR, right? It will be very noisy in realistic use cases. If you have transmitter and receiver indoors, it is always going to look this jumbled up, right? So apart from, as I told you, apart from reporting the time of arrival value, you are free to also report some kind of an uncertainty that is associated with the range, right? You can tell that, okay, I think it is 10 meters, but please add an error margin of plus minus 2 meters, so that you report your localization algorithm, you can anticipate that particular noise, right? So maybe you can fuse this information with the previous range estimate. The previous range estimate was probably 11.5, and now it has become 10, right? So based on some of the historical data, you can also smooth out this value. Okay, that is also possible, and that is really useful in tracking scenarios. If you keep on getting such range values, and that is having a lot of noise in it, in that case what will happen, you can use very simple smoothing filters, right? You can use smoothing filters. We are going to look at some of these examples of smoothing filters when we discuss inertial sensors. One example that is very commonly used is Kalman filter, right? So uh, Kalman filter could be used for removing such errors. Okay, so but you have to be very careful. You don't want to run something which is very computation heavy. We have to really do this within a very short span of time, and after that the next packet is going to arrive. So there is always a trade-off. You cannot delay arriving the next packet by a huge margin because you are so busy computing the time of flight. You cannot do that because your update rate is going to go down. If you are only able to process this entire data in 1 second, now think about it, you have to do three ranges per to compute the, at least three ranges to compute the location, so you'll take 3 seconds, right? So in 3 seconds, if it takes to compute one location update, that is a terrible performance, right? So before in 3 seconds the device have moved, right? So what I am meaning to say is the device was here when you calculated range number 1. In second number 1, the device has moved now. In second number 2, time instant 2, you have calculated range 2. Okay, and in second 3, you have calculated let's say range 3. So none of them are consistent. Range 1 was for this location, range 2 is for this location, range 3 is for this location, and the device moves on. So the latency that is going to be required for computing this range should not be very high. It should be in the order of like let's say a few hundred milliseconds. By that time you should be done computing the location, right? I'm not considering very high speed entities. So all these IoT devices I am thinking are like robots or human beings that interact with humans, right? It interact with us, right? It's not like a drone that is moving at a very, very fast speed, right? So in that case, this kind of smearing is going to happen. Okay, so this is an effect of smoothing, right? If you smooth things out, it will be very clean, right? And higher sampling rate, right, is going to improve the resolution of this time, right? You can very easily understand, right? If you want a low value of delta t, right, that is what we want, the resolution of this CIR. So if you want a better resolution, which is in picoseconds, which is in tens of picoseconds, that resolution means that you are actually having a more number of samples per unit time being collected, right? So that smaller is this delta t, which basically means higher is your sampling rate. Okay, so you'll have more samples, you'll have more samples per unit time, and then only you can ensure that the difference in between these particular samples in the time domain is less. Okay, if you have a lower sample rate, right, let's say you collect data like this, which basically means your delta t is now higher, which means that you are going to have a poorer resolution. It is not going to be in nanoseconds, maybe it is like tens of nanoseconds. Okay, so everything depends on the sampling rate, and that basically means what is the bandwidth of the signal. You have all I am guessing you have some basic background in computer networks or digital communication systems, right? I mean second year kind of material for BTech. Okay, so you are all aware of this particular thing, that higher the sampling rate is going to be ending up in a higher signal bandwidth, and that is the reason sometimes some of the technology like ultra wideband is going to give you an excellent resolution. That is the reason you can obtain a range with centimeter level accuracy, right? So if your bandwidth, let's say, is in gigahertz, okay, versus your bandwidth is in megahertz, right, that makes a lot of difference. So if you have a 20 megahertz bandwidth signal, right, which is often the case for the first generation Wi-Fi. We in ABG, right, we used to have a 20 megahertz, then it became 40, then it became 80. Now we also have 160 megahertz channel width, right? So still it is in tens of megahertz, and that is fundamentally going to limit your distance resolution to meters, right? It cannot go better than that. It cannot become like centimeter, right, using a 20 megahertz bandwidth signal. Whereas if you are using ultra wideband and you are using something like 1 gigahertz, right, so in that case you can expect sub meter sort of a resolution. Okay, and then you can employ, so on top of that you can also employ noise filtering techniques, right? Let's say you compute not just one range, but you compute, let's say, 10 ranges per unit, like whatever time you are allowed to do this range acquisition. And after, like, let's say after collecting 10 CIR samples, you place them together and figure out by filtering out the noise that this is the exact value of your that is the exact offset of your first peak, right? So that is possible. So that actually makes some improvement on the accuracy. Okay, so now we have a good idea about trying to record the exact timestamp. Okay, so now we are going to look at a way in which this clock offset can be corrected, right? How the protocol can directly help you in correcting the clock offsets. Okay, so we have not yet looked at it, right? We have just known the packet arrival time, but we need to make sure that we are getting the packet arrival time precise. Let's say what is the time taken for the signal to travel from the transmitter to the receiver. That is somehow we can compute that, but your devices also will have local timestamps. What to do about it, right? How can we make this ranging procedure agnostic of the clock offsets or the clock drifts? Okay, so let us look at a synchronization algorithm, and this is a very common algorithm that will be employed in such devices. Okay, this is known as two-way ranging, but let us go through it, right? Let us take the pain to understand how this works. Okay, so again the setting is same. You have the transmitter, you have the receiver, TX, RX. This is the timeline. The vertical thing is the timeline. Okay, this is the time axis, and this is also the time axis. So various things happen at time t1, that is somehow recorded by the hardware of this transmitter device, right? In the radio itself, uh, it is possible to record the timestamp, right? I was telling you that to bring the timestamp as close to the uh, radio as possible. So some of the radios today, they will allow timestamping in the radio itself. Okay, so T1 is recorded in that way. And what is the packet arrival time? So T2 minus T1. So T2 you have received the packet, T1 you have sent the packet, minus delta clock. So there will be some clock drift. Okay, and that clock drift is going to be compensated here, right? So another thing you can simply do is you can also look at rho as T4 minus T3 plus clock drift, right? Because let's say instead of sending one packet from the, let's say I call it transmitter, or it is A, and our receiver is B in this case. Now B becomes the transmitter and B sends a packet at time instant T3, okay, which is received by A at time instant T4. Okay, so in this case also rho is equal to T4 minus T3. This is T4, time T4, this is time T3. So T4 minus T3 is going to give me rho, but there is a clock drift, right? So because we thought that either one of them is lagging behind, or it is ahead of the other one. So that is the reason the sign here has changed. If you notice carefully, I have used a minus clock because I'm not sure which one is lagging or which one is moving ahead, right? But since the direction of the data exchange has reversed, right, so I have to change the sign of delta clock. Okay, and now we have these two instances, right, of row, and if we simply add them we can get like 2 row, right? So 2 row is equal to t2 minus t1 minus delta clock plus t4 minus t3 plus delta clock. So I somehow got a magical way to compensate for this clock offset, right? So in this way you can add up these things, right? So in case of GPS, remember that I was not sending out a signal that is going to be received by the GPS transmitter. It was not possible. So GPS is going to send out only broadcasts that is being received by everybody on Earth. In this case, I have the luxury to send out a message that to the transmitter. So in that case, we did not have such luxury. So we have to deal with that clock drift in a different way. In this case, I have this luxury. I will use this for leveraging or correcting my clock offset or clock drift, right? So T2 minus T1 and this T4 minus T3 divided by 2, that actually gives me the value of the range, or not the range, this is your time of flight or time of arrival. Okay. So my question is, what exactly is the fallacy here? Is it everything is fine, or do you think there can be something that goes wrong here? So are you fine with this algorithm?
There is a
Do you
time delay
think?
between sir T2 and T3.
Can you repeat, sir?
Sir, there is a time delay between T2 and T3.
There is a time delay between T2 and T3. Okay, but
Sir,
how does it matter?
sir, it may cause the sir.
No, how
Error.
does it matter? I mean, fine, there will be a time. This is a computing time delay, right? There is a time delay of X.
Sir, it can cause an error, sir.
How?
Sir, because we are dealing with nanosecond.
No, that is fine. Let us deal with nanoseconds. But how does T3 minus T2 come into play? I am saying this is T2 minus T1 minus clock offset for this row, right? We are done, and then I am doing a separate computation that is starting from T3. This could be even 1 minute. How does it matter? That's not the reason.
So packet time will get affected.
No. Be very precise what you say, right? Because I am really talking in like kind of layman terms, right? This is a very like let's not bring any jargons here, right? So I am telling you that I am transmitting a packet at time t1. It is being received at t2. I am calculating range as t2 minus t1 minus delta clock. Absolutely clear, right? It's doing the same for t4 and t3. T4 minus t3 plus delta clock. I added them up. Delta clock gets cancelled, and I took an average. I did it divided by 2, and so I get a row. So my question is that of course, there will be some issues with this assumption, right? What is the assumption that I am making here? That is the question.
Sir, is it any change of the transmitter? Like as you told, another that signal may be channelized through other transmitter or anything?
No. I don't imagine anything that is beyond this slide. Don't bring up anything.
Considering only LOS.
Every LOS. Let's say just LOS is there. Okay, so let me give out the answer, right? So the assumption here is primarily that we are going to assuming here that there is no clock drift. The clock drifts are going to change. So the clock is running here at A, the clock is running here at B. So at this point in time from T1 minus T2, the clock drift was delta clock. But when I am using the next equation, T4 minus T3, I'm using the same delta clock. This delta clock will become some delta clock 1 because clocks drift. So this will be delta clock 2, right? And that is the reason we cannot simply do this cancellation. Okay. So I think that is the mistake that we have done, right? It has nothing directly to do with the time period from T2 minus the T2 and T3. This can wait, but there is a clock that has drifted in this time, right? Both in A and B, right? So I was using this term A and B. That's why we cannot simply cancel them. Okay, we have assumed that the clock drift has remained same, which is not true. Okay, so this is a serious problem, and in case of your GPS, always try to connect the dots, right? Otherwise you will not have a holistic understanding. So in case of GPS, there was no clock drift in the transmitter, so it actually saved us in certain way. There was no clock drift in the transmitter. Clock drift was only happening in the receiver, so I only have to deal with myself, right? That's why we introduced one more equation, having this variable delta clock, right? And here we are trying to solve that itself in the protocol. We'll see how it is getting solved. Okay, so this is something that I have already told you in the last class, is that you can do a simple experiment where your time ticks, and I am increasing the counter value by 1 with every clock pulse, right? And you should ideally expect something like this, right? The gradient being the frequency. Okay, how many counts per second you are increasing, so that is your f, or the frequency. Okay, however, in the real world it is not going to behave in this way. In the real world it is going to behave in this way. Sometimes the clocks can become slow, sometimes the clocks can become fast, it can slow down. There are a lot of things that can happen, which is far from ideal. So this is an ideal scenario. There is no drift. Okay, but in a scenario where like things can become warm, like even the temperature of the CPU can influence the drifts, right? It's very, very sensitive. Okay, so, and particularly we are not using any high class CPUs in IoT devices. That is what I also brought up in the last class. We are primarily looking at IoT devices that are very cheap. Okay, and it has a microcontroller that probably costs a few hundred rupees, right? Or even less than that. Okay, so don't expect a processor that is going to give you a very, very accurate clock, right? So clocks will make mistakes, there will be drifts, and we have to embrace that. Okay, and the challenge is how to design a technology that is going to embrace these cheap devices and still give you a good value of the range. In our context, good value of range. Okay, so hope this is clear. And now we have to, basically we don't have any other option. We have to embrace this clock drift and progress. So instead of using T1 directly, we are going to use the true T1 is equal to T1 plus 1 plus delta A, where delta A is the clock drift at A. Okay, and true T2 is equal to T2 into 1 plus delta B, where delta B is again the drift. So I am accounting for the drifts here. Okay, accounting for the drifts. Okay, so now I have just simply replaced the values, right? So there was no problem with the formula, right? Apart from the fact that I have just cancelled these things out, right? Which was objectionable, right? So other than that, I did not make a grave mistake. I simply took these two values and averaged them out. So I am free to write this equation again. Okay, I have, instead of using the value of T1 or T2 directly, I have now clubbed it with this drift as well. Okay, so if you see, when I use T1, I am using the value of true T1. When I am using T4, so T1 and T4, I am again using the drift value. Okay, so I am assuming the clocks are drifting. So T4 1 plus delta A, and same for T2. I am using delta B. Okay, so with this, let us see what happens. So I am simply rearranging the terms. T2 minus T1 plus T4 minus T3, this becomes free. Okay, and on the right hand side I have this T2 delta B minus T1 delta A, and so on, right? And just focus on the equations, right? There are lots of insights that you will start getting, right? I will be asking you about some of these insights. So concentrate on this equation. I am going to copy this equation to the next slide. So we have this thing built up, right? So this is the thing that I'm just refreshing your memory, right? And then I'm trying to exchange some of these terms, right? I'm basically going to club the delta b's together. So I have marked them with this red ink. So T2 delta B, T3 delta B, and T4 delta A, T1 delta A. So these are the things that are associated with the node B, and these are the things that are associated with node A. Okay. So delta B, I take common, T2 minus T3 plus delta A, T4 minus T1. Copy this to the next slide. Now, what I am doing is T4. What is T4? So what I am doing here is this T4 minus T1, concentrate only on this part of the equation. So what is T4 minus T1? T4 minus T1 is basically this time gap. Okay, so what is this time gap? This time gap is twice of rho. So because the packet has traveled 2 times, so this is like round trip time. So 2 rho is basically your round trip time plus T3 minus T2. Okay, there was some time that was spent here, right? So T3 minus T2. So this is, I think, is clear. T4 minus T1 could be written like this: T3 minus T2 plus twice of rho. So this is one row, this is another row, and this is your T3 minus T2. Totally, it becomes T4 minus T1. This entire gap. Okay. So I hope there is no issues in understanding how we can rewrite this equation like this. And you can simply shift these variables, right? So there is this delta A into 2 rho. There is one part, and there is a delta A minus delta B multiplied by T3 minus T2. Okay. Now what can be done is this is going to be lesser value, right? So the magnitude of this value is going to be very less. So this is like a drift multiplied by the time of flight. Okay, so this is like very small quantity which could be ignored. Okay, so whenever you start ignoring something, you have to understand at what level we are dealing with, right? So the time of flight, let's say we are trying to have a resolution from the CIR which is in nanoseconds, right? And let's say the drift is in microseconds. Okay, so or even less than that, right? So micro and nano multiplied, right? That is acceptable. Well, this is really small. We are dealing with 10 to the power minus 15, minus 14, and so on. Right? That is fine. Okay, and you have to have a proper justification of why are you ignoring a certain term. Okay, so this is very small. I have actually written it in the slide. It's very small, and you can ignore it. Okay, so now we are left with this. Okay, so the rho is equal to this thing plus delta A minus delta B multiplied by T3 minus T2. Okay, so this is basically your processing time, right? T3 minus T2 is the computation time or the processing time. Computation time or the processing time. Okay, so now we are basically facing an issue. Because why we are facing an issue? Why do you think it is a problem? Because devices could be heterogeneous, right? It's not that all sorts of devices, all the IoT devices that you have, and where you want to implement such localization framework, right? They are going to have equivalent processing times, right? So now the error that you are going to introduce in the system is going to depend on the processing time. Okay, and then B could be a smartwatch, or B could be a smart TV, right? A smartwatch is very much resource constrained, and it might actually take a long time in processing this information. And T3 minus T2 be quite large. Okay, even these drifts are there, right? So at least we have taken a difference of drifts, which basically makes this quantity very small, right? But this could be large. T3 minus T2 could be large. There will be some computation that you are doing, and this computation might not be done in a few microseconds. It might take more than that, right? So in that case, it is a function of the processing time in the one of the nodes, right? And so you will have ranges being computed, which is a function of the processing time. We should not be ideally allowing that. Okay. So because why is this processing taking some time? Because the radio needs to receive and decode the packet and hand it over to the NIC card, right? So kernel needs to receive and record the packet, and if there is a kernel or if there is a firmware that is simply running in the microcontroller, that is also that has to do some of these tasks, right? uh, Although it's not a full-fledged operating system, still it is going to do some of these things. Okay, and this error can become quite large and it can run to meters, right? Still we are talking about meters, right? We are not talking about kilometers. So because this value is quite small, it is helping us, right? And this is multiplied by a large number, so the number is kind of a moderate value, moderate magnitude. Okay, so still we have some idea. It has I have somehow handled the situation, but this is not, we are not quite happy, we can still do better. Okay, this looks reasonable. If you are happy with a few meters accuracy, you can go ahead with this particular thing, right? And let's say, or if you know the computation time beforehand, right, you can always adjust that value. Okay, so and you know that it is homogeneous across all the devices, you can do all such things, right? But is there a way that I can do better? Okay, so instead of just having this one-sided transmission where A is transmitting to B and this thing, right, we repeat the process again, right? As you saw right here, we were taking this thing, right, T3 minus T2 into consideration. What we are trying to do, can we bring some symmetric action on the other side also, so that somehow using a trick we can get rid of this computation time. Okay, so now what we will do is that we have one more packet, or one more packet that is going to be transmitted from A to B, right? So once I receive this T4 at time T4, I take a certain gap, right? So there is one more computation that is being done, and the time taken is D underscore A, or D subscript A. And at time T5, I send out the packet. And once it reaches the other side B, the time becomes TC. T6, sorry, T6. Okay, so now what is the packet arrival time? How can we write it? Just concentrate on the top equation, RA minus DB. Okay, so RA minus DB is this particular small time, right? And RB minus DA. So RB is basically this entire snapshot of time, and DA is the small part, right? So RB minus DA is going to give you this 2 times the value of rho. So this is the 2 times the value of rho, and RA minus DB is going to give you 2 times the value of rho. So one is here, one is like, you can draw it here. So this is the first copy, this is the second copy, this is the third copy, and this is the fourth copy, and that is why we divide it by the value 4. Okay, so there are like 4 times rho has gone into this particular equation. Okay, and I have just, instead of using this RA, I have also used the clock drift. So RA is being multiplied by 1 plus delta A, and similarly for the node B. So DB and RB is going to be multiplied by delta B. Okay, and delta A is going to be used for these 2 transmissions for A. Okay, hope I am hoping this is clear, right? Why 4? Why 4 is clear for all?
Yes, sir.
Okay, very good. So 2 and 3, note that it is overlapping. So 2 and 3 are not separate time instance. It's the same time instance, but it was calculated twice, right? Because some RA accounts for that and RB also accounts for that. This is a common region. So this common region comes twice. That is why it's actually 2 and 3 are equivalent. So 1 row from here, 2 rows from here, and 1 row from here. That's so 4 divided by 4. Okay. So now again the same algebra we have to do. RB minus, so just concentrate on the main part. right, where we are really interested in looking at correcting for the clock drifts, right? So keeping on arranging like the previous time. So this part is clear, this part is clear. RA delta A, we have grouped them together like the previous time. Okay, so similar to the previous time, I have also expanded this RA delta A minus DA delta A in this way, right? So DA delta remains the same. RA delta is basically DB delta A plus twice rho delta. You can simply look at the picture and very easily you can figure out how this expansion takes place. Okay, and now we come to this situation, and this dB minus dA, and there is a sign change. We can simply do this, right? So earlier there was, if you compare this to this previous equation, where there was still this delta A minus delta B, but T3 minus T2 was there. Okay, which was basically the computation time on the second device, on the B device. Okay, but now this is dB minus dA. Okay, so what is dB minus dA? Let us go back to the picture. So this is dB and this is dA. Now instead of depending on dB or dA, it is depending on the difference of dB and dA. Earlier it was T3 minus T2 that was actually bothering us because this could have been large. Now we are concentrating or we are making the equation dependent on the difference of the computation time, right? Multiplied by the difference of the drifts. So earlier this particular part was small, right? But since it was the raw computation time, this was large. Now I have made it dependent on the difference of the computation time. So this will be small. Okay, so maybe one of them takes let's say some microseconds, and then it is if you are trying to do the same job, because all these devices are running the same code, right? So we might try to do or make the computation time as same as possible, because we can give the minimum amount of job within the particular time slots, right? So not a generic work, because this is particularly this job, right, when it receives the packet and when it sends out the packet. So within that we can try to do as less job as possible, right? And this will make this time smaller, and the difference anyway will be smaller. Okay, so the difference in between dA and dB will be smaller. Okay, so now from a few meters, in this way you can experimentally, this kind of things have been proven, right? And you can reduce the error to a few centimeters. Okay, and these devices could be programmed to have the approximately same turnaround times. Okay, so as long dB is approximately equal to dA, okay, if dB is approximately equal to dA, then you basically don't have any errors, right? But sometimes it is not possible to guarantee that, right? So since it's anyway a small number, it can give you a very good accuracy. And now you kind of know that what is the secret trick to actually have a wireless ranging mechanism involved to get an accuracy of few centimeters, right? So how involved is the process, what is the way to get the exact packet arrival time, how do you implement synchronization, right? Now we don't require a third equation or a fourth equation or a fourth access point in order to correct for the clock drifts, right? So we embedded this concept itself in the ranging procedure. Okay, and this is known as symmetric two-way ranging, because we are assuming that the system is symmetric, right? Whatever is the row from this side to that side, and the same row is going to be the other side as well, right? So, and whatever A does, B also repeats the same thing, right? So the symmetricity is going to take away a lot of these things that we want to get rid of. Okay, and it is two-way ranging. A does ranging to B, and sort of B also tries to range A, and in that way we get a more correct value of the range. Okay, so remember, this is very commonly known as TWR, or two-way ranging procedure. Okay, and this is not the end, right? If you look at company manuals where they sometimes tell you how exactly they are trying to compute the time of flight, it can even become much more complicated. Say they want to go from a few centimeters to like 1 centimeter or less than 1 centimeter, right, or millimeters. Okay, so there could be a little bit more involved way, right? Suppose you, instead of doing 2 times, you do a third time, right? And you can try to explore that how can you reduce the ranging, right? Suppose you are extremely sensitive to this range value, right, and you have enough time so that you don't have to hurry, right? Because more the number of these exchanges, more is the total time that is required for ranging. This is the ranging time. So if you have many such packet exchanges, your throughput is going to come down, because A and B is taking so much time, C and D are waiting, right? So only after A and B is done, you have to range C and D, or A has to range with other beacons, right, or other anchors. So you cannot spend a whole lot of time just by finishing this ranging procedure and make it very accurate. So there is always a trade-off in such systems. How precise is the range and what is the location update rate. Okay, so this precision, okay, I would rather use the word accuracy, because the precision is sort of determined by the resolution that is given by the system. So it is rather how accurate you want to have the range, right, versus the location update rate, or I would say latency. Okay, so what kind of latency you are happy with? Somebody tells you that I need a location update every 1 second. So in that time, 1 second is a lot of time. So you can actually have a more complicated ranging procedure, which is going to bump up your accuracy. But somebody tells you that, okay, I want to have a location update rate every location update every 100 millisecond, right? That is like at the rate of 10 hertz. So you have to complete this entire ranging procedure, run the algorithm within 100 milliseconds, right? So in 100 millisecond, you have to range with 3 anchors, plus you have to compute the location. All of these things has to be done within 100 milliseconds. Otherwise, you will not satisfy the SLA, right? The service level agreements that you have with the application. So this is the design part that you will face, right? What kind of parameters you want to choose. Okay, so instead of 3 anchors, it could be 4 anchors, 5 anchors. You have to like decide it accordingly. Okay, so that is one more input that I wanted to give you. So I'll go through Wi-Fi example, right? Wi-Fi fine time measurement. This is recently been introduced in the Wi-Fi standards, right? So some of these radios have the capability to expose ranges, right? And it's not that all Wi-Fi chips is going to support that. Android 9, I think it is known as Pi or something, right? Android 9 and more than that, right? It has support for supporting Wi-Fi ranging. So it is Wi-Fi FTM, fine time measurement, or it often is known as, in terms of time, it is RTT, round trip time, right? So, and the standard that is being specified in the documentation you can look at is 802.11 MC. Okay, so this is what that dictates what kind of this ranging procedure, and some of the chips enable that, right? So this is not mandatory. This is probably an optional thing. That is why not all the vendors do it, right? But there are some common access points that will support and respond to ranging requests. So what will happen is, let me show you the picture here, right? So this is your Android smartphone on the right hand side, right? That has this Android 9 plus, and it has support for these APIs. And this is an access point that is FTM enabled. We often call it FTM enabled. Okay, fine time measurement enabled, right? And it is going to compute the round trip time. And of course, depending on the resolution, right, that we can achieve, depends on the bandwidth, right? So although they might, some of the industry standards, like some of these access points might claim that they are going to give you a very good resolution, but that resolution cannot just be obtained as a function of a bandwidth, right? Because the bandwidth will still be 80 megahertz. Okay, and the 80 megahertz is going to determine what is the exact temporal resolution that you are going to achieve in the channel impulse response. But what you can do is that you can do on top of this, you can do a lot of filtering, as I have already told you. Okay, you can get multiple snapshots of the channel impulse response, and by using that you can reduce the noise to a great extent. Okay, so yeah, as I told you, Android Pie Plus, it is going to be supported, and you can have applications that are actually available in order to get such ranges. So either you can use this, if you are familiar with the Android development platform, you can simply use these APIs to get these ranges from the access point. Okay, please note that not all access points are going to support that, but some of the access points that are on the higher end, right? Some of the Aruba access points, for example, it will support that, and you can get the list of access points that will support this fine time measurement in the Google developers web page also. If you go to this Android developers web page, that discusses on this FTM or Wi-Fi RTT, you can get a list of access points that are currently supported. Okay, so one of this is this CompuLab Wild, right? I do happen to use this one, so I have this recently purchased, right? Currently they are stopping production of this particular hardware, but you can also get other APs, particularly some of this Aruba 510 series, right? Or more than that. This is anyway expensive, so there are 530 series, 540 series also. They all support FTM. Okay, so you can simply buy one of those and try out this ranging procedure. And these are the Google devices, so Google Nest or some of this Google this mesh routers that they sell. This is also a little bit expensive, right? So you might try to get some of these Aruba access points that are available at a much lower cost, and try to find out like which one, like what are the allowed access points and that fits your budget, right? And same for the smartphones, right? Not all smartphones are going to support FTM. Okay, so also find this list in the Google developer. They have nicely listed a collection of smartphones that support this fine time measurement. Okay, so most APs will use one of these two things. Either it would be a Broadcom chip or it's a Qualcomm chip, right? So unfortunately, I have not come across Cisco router still supporting FTM. I have primarily looked at Aruba, which does support FTM. Okay, but in the future they could be added, right? So it is not yet pervasively available across all access points, but starting to kind of getting rolled out. And one important thing that you have to keep in mind in case of Wi-Fi FTM, because of privacy reasons, the access point is not going to have any access to your range data. Okay, it is going to help you in ranging, right? It is going to do all this two-way ranging and so on, right? But it is only your smartphone or your IoT device that is equipped with the relevant Wi-Fi chip, right? That can only have access to this range information. So that is how they have designed this Wi-Fi FTM such that there is no issues with privacy, right? Otherwise, what will happen, right? If in case of any big airport or shopping mall, I can simply deploy such APs and I can localize every person, right? So that will be kind of a breach of privacy. And if this person connects to my hotspot, I can even know their MAC ID. In that way, I can identify a particular person, right? So they don't allow it easily, right? So in the protocol itself, there is no mechanism for the AP to know your range. Only if you, through a particular app, you report this information back, right? You report this XY back to this AP, then only you can know. I mean, then only the infrastructure side can know. Otherwise, there is no such data leak that might happen. Okay, so you can read up more about these things, because in the next generation shopping malls, you can have a small chip that could go onto your shopping cart, right? Or any other places that you want to be sort of location enabled. This is a very good option, because Wi-Fi access points is more pervasive, right? It's not any extra kind of hardware that you have to just get for localization. So this is already there, and it will be installed for communication purposes, right? Particularly in places like airports or big shopping malls. And it is like primarily you often need to track yourself, right? Because often you will go to an unknown place and you will see a big map that's saying that you are here, right? And that map you have to somehow keep on in your mind, or you can take a picture of that particular map and then navigate, right? Suppose you want to go to the bathroom, or you want to go to the some food corner, right? In that way you have to basically zoom in the map and see what is going on. There is no navigation that is enabled. But if you have this Wi-Fi FTM being deployed in the future generation of this Wi-Fi deployments, right? Enterprise Wi-Fi, Wi-Fi in these big places like airports, we can have this inherent navigation also integrated. Okay. So some of the APIs, but I would request you to actually, if you are interested in coding these things up, right, I would actually request you to go to the relevant website, right? I have given you this Android connectivity. They have some samples for doing this Wi-Fi RTT scan, right? You can trying to figure out the distance from that AP. So there is a way to request the distance and receive the distance from the access point and locate the actual position. Please try to go through them, and if you are interested, please try to implement them. Most of these codes, the sample codes, everything is open source. Okay. So instead of me feeding you with all the code, right, please do some of your due diligence in order to figure out where these things are available, right? In that way you learn more, right? I could have given you a sample code and you just run that and you are done, right? Instead of that, please take the pain to go through the developer manual and try to see where things are, right? So that gives you a lot of context, and you will have a better understanding of the different features and the different functionalities that are available today. Okay. And I might be like, this could be a little bit dated, right? Whatever I am telling you, right? Things might have moved on. You might actually have something that is much more smarter than whatever I am telling you, right? So I do request you to, at least this is something that you can do, right? So if you do not want to get involved with the channel impulse response type of data, this kind of things, you can already buy a smartphone, you can buy an access point and try this out. Okay. So so the sample app, right, I have given you the link. You can download and try it out. And I would suggest that if you have background in Android, right, why don't you try to recreate this particular application, right? And this just does ranging. There is no localization yet, right? So what you can do, you can use the code from this particular app and implement localization. What this particular app is trying to do is that, given your smartphone and given this access point ID, it is going to find out the distance. That's all. Now you can create an application, right, where you have the you can have these hard coded values of the access points location, x1 y1, you have one more x2 y2, and you have x3 y3, and you should ideally show me a real-time map of how this person is navigating. Okay. So the simple small project, it is not like a major thing, right? So already most of these things are there, right? And if you simply do this, right, you try to find out the track in which the person has moved, this will give you enough experience about what is the accuracy of such systems, right? You will see that it does need some betterment, right? You won't get a simple so very beautiful smooth trajectory like this. What you will end up in is something maybe like this. Okay. And you have to use other techniques of processing such data so that you can get rid of noise, you can make it smooth and all these things, right? So that is something that where you will learn a lot about the practical implementation by using Wi-Fi FTM. Okay. So I'll come to ultra wideband, and ultra wideband chip is also commercially available, and that gives you a clock resolution of 15.6 picoseconds. So now the time ticks. Now if you see, these are in picoseconds, right? And that is going to give you a millimeter level distance resolution or a granularity. Okay. So that is why I have mentioned using gigahertz bandwidth, you can do much better. right? And this is something that are used in many collision avoidance systems. This is a subway system in New York City in Manhattan, where this company called Piper was trying to have this UWB beacons that was on top of the in the front of the train, and whenever there is some other train that comes very close to it, it can signal, right? So that the trains has come very close to each other, and they should like signal. Okay, so this chip, right, can in fact give you access to the raw channel impulse response. Okay, and this is available in the Indian markets. You can buy it, right? You can simply look up Decawave UWB chip, and what you need to do is, this is just the radio, and you need to interface this radio to a microcontroller. Okay, so it will have an, let's say this is an SPI bus in the radio, and you need to look at the manual of this chip, right? And then you can schedule any sort of packet transmission, putting the timestamp in the packet, knowing the timestamp of the packet when the packet has arrived in this radio. Everything is available. Okay, so you have to program this particular thing. You have to basically implement this two-way ranging TWR in between these two Decawave UWB chips. Okay, and this also is not very costly. I mean, there is an Arduino shield that is available for this Decawave chips, which will be again costing you around 1500 rupees or so, or even less than that. I think there are many vendors who are selling it. It won't cost you, like in dollars, it's not going to cost you about, like maybe it is 12 to 15 US dollars, right? So you can get this ultra wideband radios, and very good for learning how the channel impulse response is affected by the multipath environment. So even if you forget about getting the proper value of range, you can use this for understanding the physical environment, like sensing the channel, right? And for us, this channel basically is the environment. Okay, so is it a room where there are lots of people? Is it a room which is empty? Is it a place where there is a lot of multipath? So you can start answering, apart from localization, you can start giving some context to that, right, environment. So CIR itself can be used as a sensing modality. Okay, let us not be just restricted to localization. Of course, it solves the problem of localization by giving you the fast path, but the other components that we started ignoring, it can tell you other secret information about the environment. Okay, so I will give you an idea of how this ultra wideband modality could be used in a setting where firefighters or first responders need to be detected where they are, right? So I'll give you an introduction to that, and to next day's class, right, tomorrow's class, I'm going to finish it off, right? So this is a practical application of the UWB ranging. Okay, so this was a paper that we published in Usenix NSDI 2019. You can look up the paper, right, and it has an associated video that I created. You can look at the gist of what happens, right? So I'm going to the technical part, like what are the challenges of this problem, to be exact, right? What are the real challenges that will come in the next class, in tomorrow's presentation. But today I'm just going to tell you what is the context, right? So as you know, whenever there is a big fire in some of these high-rise buildings, this becomes a challenge for the firefighters and more for the command persons who are outside. Because if you in the center, I show you this outside mobile command van, they continuously try to communicate with these people who goes inside, right? There are two reasons. One is the logistical reason. First of all, where do I want to send the troops is not clear, because I have just asked them to go inside. Now how do they coordinate after going inside? I don't know where exactly they are. Maybe I can tell you that they have gone to the 4th floor, that's all, right? Or maybe the east side, right? But I have to be very cautious for a very large building where there are many floors and it's a large area, where exactly they are to some extent, right, in terms of indoor scales, so that I can put my people in a more resource efficient way, right? We don't have to waste resources. Maybe it is a large sort of a building and most of the people are concentrated here, most of the firefighters are here, okay, where this part there is a lot of people who needs to be saved, there are victims, and I don't know the location of the firefighters, so I cannot direct them to go to the right spot, okay. And even 3D is sometimes a problem. They go inside and then they try to climb stairs and so on, there are fire exit stairs, right? Sometimes I don't know which floor they are in. So it is extremely important problem that I need to localize such firefighters in this disaster scenario, okay. And this happens quite a bit, right? These days there are many accidents and injuries that these firefighters face, and often they unfortunately they lose their lives because one of the main reasons is that they start feeling unwell, and even if they report the outside command center that I am feeling unwell and I need to be evacuated, I am running out of oxygen supply, there is no direct way to reach him. I don't know where he is lying. I can go and find him, but it might take a long time, and then by that time he has lost his consciousness, right? Or sometimes something more fatal or bad things happen, right? So we really need a solution to this, and I will show you, right, how can we use a simple technique that we have studied like ultra wideband ranging in a very innovative way in order to track such firefighters in real time, okay. So that is going to be the premises of the beginning part of tomorrow's talk, right? And how we are doing it, I am going to introduce that later. Like we use drones and so on that carries ultra wideband radios and communicates with firefighters inside. It will be a very interesting system, and some of you who are enthusiasts of building systems, right, I think you will have a lot of fun in try to understand this, and if possible try to replicate things like that if you have access to resources, okay. So with this I'll like stop today's session, and I'll dedicate like whatever 15 minutes we have for answering your doubts from today's class, or in general whatever doubts you have, okay. So